1,000 years after departure, the ship would still be moving through darkness. The stars ahead might have shifted almost imperceptibly, while the sun had long since vanished into the crowded background of the galaxy. Every person who remembered Earth would be dead. Their children would be dead, along with generations of descendants who had known them only through portraits, preserved voices, and names engraved into the oldest sections of the vessel. The people alive aboard would have inherited a journey whose beginning belonged to a remote age. Around them, machines designed by forgotten engineers would continue moving air, purifying water, regulating heat, feeding roots, and holding thousands of tons of material together. Few original components would remain. Pumps would contain parts manufactured by workshops built centuries after launch. Walls would carry patches over patches, each repair marked in technical records and family memory. The ship would resemble an ancient city whose foundations had crossed the interstellar void, renewed continuously by inhabitants who could never afford to abandon it. Survival across 1,000 years would demand far more than durable technology. A society would have to preserve enough people, knowledge, discipline, freedom, and hope to keep the voyage meaningful. It would need to raise children who accepted responsibility for machinery they never chose and a destination they might never see. Every generation would inherit a world without rescue, a world whose failures could spread through the air itself. Humanity's greatest challenge between the stars would be carrying a functioning civilization through a period longer than the history of many countries. 1,000 years occupies an uncertain place in the human imagination. It appears short beside the age of a planet and overwhelming beside the length of a life. A person can understand a century through grandparents, archives, buildings, and institutions. 10 centuries extend beyond any direct chain of memory. Languages transform, religions divide, borders vanish, and entire forms of government pass from necessity into history. A mission lasting that long would contain several complete civilizations within the same moving hull. The people boarding at departure might imagine themselves as the founders of one continuous society. Their descendants would experience repeated periods of stability and disruption. Laws would be revised, forgotten, restored, and interpreted through conditions the founders never anticipated. New customs would emerge from accidents, shortages, migrations between habitat sections, and disputes over the use of finite resources. The original culture would survive through fragments woven into a society with its own historical depth. The journey would also exceed the useful life of almost every machine known at launch. Engines, computers, pressure seals, cables, bearings, medical scanners, agricultural lamps, and structural sensors would require replacement. The vessel could carry spare parts for its early decades, though no warehouse could contain every item needed across a millennium. Eventually, the passengers would have to manufacture the ship from within the ship. A 1,000-year vessel would therefore begin as a spacecraft and mature into an industrial world. Its workshops would need to refine material, produce alloys, shape components, manufacture electronics, create medicines, and rebuild the machines responsible for further manufacturing. Each generation would inherit a technological ecosystem whose weakest link could determine the fate of everyone aboard. The ship's first requirement would be a boundary strong enough to preserve pressure through centuries of impacts, vibration, thermal change, and material fatigue. Its hull would face microscopic dust traveling at immense relative speed. Radiation would alter electronics and weaken certain materials. Repeated cycles of heating and cooling would create stress within joints and seals. Tiny imperfections could grow slowly for hundreds of years before becoming dangerous. Designers might divide the vessel into many independent pressure compartments. A puncture in one section would trigger automatic doors, isolating the damaged region before the atmosphere escaped from neighboring habitats. Water tanks and storage areas could surround inhabited spaces, providing both shielding and additional barriers. Structural sensors would listen continuously for cracks, deformation, leakage, and unusual vibration. Over time, the crew would replace portions of the hull from inside or through protected external work. Large robotic systems might crawl across the vessel, removing damaged plates and attaching new layers. Some repairs would become visible features, altering the ship's original shape. Later generations might know certain regions by the family names of technicians who saved them centuries earlier. The structure would never achieve permanent safety. Its survival would depend upon inspection, repair, and the availability of suitable material. The vessel would need reserves of metals, polymers, glass, ceramics, carbon compounds, and chemical elements. Recycling could recover much of what already existed aboard, while small losses would accumulate across centuries. Matter escaping into space would be gone forever. Air would appear abundant because it surrounded every inhabitant throughout life. In reality, the atmosphere would be a manufactured mixture held within a closed container. Oxygen consumed by bodies, fires, corrosion, and industrial processes would need continuous replacement. Carbon dioxide would require removal or conversion. Trace chemicals released by plastics, plants, cleaning products, workshops, and human metabolism would gather unless filters captured them. The ship could combine mechanical life support with biological cycles. Machines would separate gases and provide precise control during emergencies. Plants, algae, and microorganisms would convert waste products into oxygen, food, and useful material. The resulting ecosystem would contain thousands of interacting processes, some designed and others emerging through evolution. A small imbalance could grow gradually. A trace contaminant might remain harmless for decades before reaching a dangerous concentration. A microbial community inside ventilation ducts could alter the chemistry of the air. Filters might function while becoming slightly less efficient with every generation of locally manufactured replacements. The inhabitants would need laboratories capable of detecting problems whose creators had never imagined. Atmospheric knowledge would become part of public culture. Children might learn the smell associated with overheated insulation or a failing purification bed. Citizens would understand that opening a sealed industrial container without permission could affect air shared across an entire district. Breathing would remain effortless, only because countless people and machines worked to preserve that illusion. Water would pass through the population repeatedly. The same molecules would move through drinking systems, human bodies, showers, crops, humidity collectors, waste processors, and purification chambers. A cup held by a child during the 8th century might contain water carried aboard at launch, filtered through thousands of lives before reaching that moment. Recycling would need exceptional efficiency, yet perfection would remain unattainable. Moisture could become trapped inside materials, lost during repairs, expelled through airlocks, or chemically bound within waste that could not be recovered safely. The vessel would require reserves and processes capable of extracting water from stored substances or captured material. A ship crossing empty interstellar space would have few opportunities to replenish what escaped. Purification systems would remove salts, organic compounds, pathogens, metals, and industrial contamination. Membranes, catalysts, distillation chambers, and biological filters would degrade. Replacement materials would have to match strict standards because a minor manufacturing defect could contaminate the entire water loop. Access to water would shape politics. During normal periods, inhabitants might enjoy gardens, bathing facilities, and decorative pools. A system failure could lead to immediate restrictions, revealing the calculated quantity behind every ordinary use. Water inspectors and life support engineers would hold immense responsibility. Their authority would need transparency, since any group controlling water could influence every household aboard. Food production would occupy a large portion of the vessel. Stored supplies could support the first years and provide emergency reserves. A 1,000-year voyage would depend upon crops grown continuously through hundreds of thousands of harvests. Agriculture would have to function without natural soil replenished by weather, rivers, geological erosion, and the wider biosphere of a planet. Plants might grow in carefully monitored substrates or nutrient-rich water. Artificial light would follow schedules designed for efficient photosynthesis. Carbon dioxide from human breath would feed leaves, while plant waste and human waste returned nutrients through controlled microbial systems. Every meal would emerge from a loop connecting bodies, machines, chemistry, and living organisms. Crop diversity would provide resilience. A disease that destroyed one variety should leave others available. Seeds would be stored in protected archives, tested regularly, and regenerated before aging reduced their viability. Genetic records could allow damaged varieties to be reconstructed or adapted to changing conditions. The passengers would also cultivate fungi, algae, bacteria, and perhaps small animals whose ecological cost remained manageable. Fermentation could transform simple ingredients into a wider range of flavors and nutrients. Cultured tissues might provide foods resembling meat without maintaining large animal populations. Cuisine would evolve according to biological efficiency, cultural memory, and the ingredients that survived each century. An agricultural collapse could threaten the population within months. Plants are vulnerable to pathogens, nutrient imbalance, temperature errors, genetic decline, and failures in lighting or irrigation. A single crop chamber might be isolated quickly, though infections could spread through air, water, tools, and workers before symptoms appeared. The ship would maintain several agricultural zones with separate systems. Their physical distance would reduce the chance that one event destroyed the entire food supply. Farmers would use strict quarantine procedures when moving seeds, equipment, or living samples between habitats. Some areas might preserve older crop lines that remained isolated from everyday cultivation. Emergency food reserves would provide time for recovery. Dry grains, preserved proteins, oils, and concentrated nutrients could last for years under controlled conditions. These reserves would require rotation because packaging degrades and chemical changes continue slowly. Every generation would consume part of the archive and replace it with new production. Agriculture would also carry psychological value. Gardens would offer color, scent, seasonal change, and contact with living systems that responded to human care. A society surrounded by metal and darkness might treat cultivation as science, labor, art, and spiritual practice. When crops suffered, the crisis would affect morale alongside nutrition. The ship's electrical power system would serve as the foundation beneath every other system. Without power, air circulation would slow, lights would fail, temperatures would drift, and communication between compartments would disappear. Even a brief interruption could damage sensitive crops, medical equipment, and manufacturing processes. A mission traveling far from stars could not rely continuously upon sunlight. Nuclear systems or another dense energy source would need to operate across centuries. Reactors would require fuel, cooling, shielding, control mechanisms, and eventual replacement. The vessel might carry several independent power stations, allowing one to shut down while others maintained essential services. Building a new reactor aboard would demand extraordinary industrial capability. Components exposed to radiation and heat require precise materials. Control systems must remain reliable under conditions where failure could poison large sections of the habitat. The crew would need to preserve nuclear physics, metallurgy, chemistry, and engineering through every period of social change. Power shortages would force priorities. Life support and medical systems would receive energy before entertainment, research, or spacious residential districts. A severe crisis could darken entire sections of the vessel. People born in a brightly illuminated age might spend their later lives inside a smaller, colder world while engineers struggled to restore capacity. Waste heat would present a quieter problem. Every reactor, computer, lamp, body, and industrial machine converts useful energy into heat. On Earth, the atmosphere, oceans, and ground absorb and redistribute it. A spacecraft can release heat mainly through radiation from large external surfaces. Radiators would extend beyond the protected hull, making them vulnerable to impacts and mechanical failure. Their fluids could leak. Their surfaces could degrade under radiation and contamination. A loss of cooling capacity could force the crew to shut down power systems even when fuel remained abundant. The thermal design would need redundancy and modular replacement. Robots might manufacture and unfold new radiator panels. Industrial schedules would account for how much heat the ship could safely reject at any moment. Energy use would become constrained by cooling as much as by generation. Inhabitants might experience this through rules whose physical origin remained invisible. Heavy manufacturing could operate during certain hours. Habitat temperatures might rise slightly during reactor maintenance. A festival involving extensive lighting could require energy approval months in advance. The cold darkness outside would offer no simple escape from internal heat. Mechanical systems would age through friction, vibration, corrosion, radiation, chemical exposure, and repeated use. Bearings wear, lubricants change, pumps develop cavities and leaks. Electrical contacts accumulate damage. Valves that opened perfectly for 200 years may fail during the next cycle. The ship would need continuous maintenance on a scale approaching reconstruction. Components would be designed for access, inspection, and replacement. Decorative panels and residential walls might conceal standardized service corridors. Every pipe, cable, and structural connection would carry an identification linked to centuries of records. Standardization would reduce the number of unique parts. Motors, valves, fasteners, sensors, and control modules could share common designs across many systems. A manufacturing workshop capable of producing one reliable component could support hundreds of applications. Simplicity would gain value because complex machines are harder to diagnose and rebuild. Later generations might simplify systems created at launch. An elegant device containing rare materials and microscopic structures could be replaced by a larger machine that the local industry could manufacture reliably. The vessel would evolve toward technology suited to its own closed economy. Performance might decline in some areas while repairability improved. Electronics would require a complete internal manufacturing chain. Computers fail through radiation, aging, heat, and microscopic defects. Stored replacements would eventually become unusable. Preserving digital civilization for a millennium would require the ability to produce processors, memory, sensors, displays, and communication systems. Advanced semiconductor fabrication demands exceptionally pure materials, precise chemistry, controlled environments, and complicated equipment. Each fabrication machine depends upon other machines. A failure within one layer could prevent replacement of components needed to repair the failed layer itself. The ship might preserve several levels of technology. Highly advanced computers would perform scientific modeling and artificial intelligence tasks. Simpler, more robust systems would control life support and critical machinery. Mechanical backups and analog instruments could remain available for emergencies. Knowledge might also be stored in durable printed or engraved forms accessible without electronic readers. A period of technological decline would remain possible. The population could lose the ability to manufacture its most advanced processors and rely upon older reserves while rebuilding skills. Certain artificial systems might become slower or less capable. The passengers would discover that technological progress aboard a closed ship could move in both directions. Manufacturing would turn raw material into survival. The vessel might begin with warehouses of metal, carbon compounds, ceramics, specialized chemicals, and rare elements. Every repair would draw from those reserves or from components dismantled elsewhere. Recycling would become the central industry of the ship. An abandoned vehicle could become a source of aluminium. Broken furniture might return polymers and metals to fabrication. Electronic devices would be disassembled to recover copper, gold, silicon, and rare elements. Nothing would become waste until every possible use had been considered. Material purity would matter. Recycled alloys can accumulate contaminants. Plastics degrade during repeated processing. Some chemical compounds become difficult to separate after use. The ship's industrial planners would track atoms almost as carefully as accountants once tracked money. Additive manufacturing could produce many shapes, though certain components require forging, machining, coating, heat treatment, and microscopic precision. Workshops would include a wide range of processes. Their workers would occupy a position similar to miners, factory operators, and infrastructure engineers combined within one profession. The engines driving the ship might operate during departure and arrival while remaining quiet through most of the voyage. A coasting vessel would still need attitude control, navigation corrections, and protection from hazards. Propulsion equipment sleeping for centuries must awaken reliably when required. Long inactivity creates its own risks. Fuel can alter storage conditions. Seals can deteriorate. Moving parts may seize. Control software may be rewritten repeatedly, creating compatibility problems with ancient hardware. Engineers would inspect and test portions of the propulsion system throughout the journey, consuming limited resources to preserve machinery rarely used. The destination might require enormous deceleration. A failure discovered during the final century could leave the vessel moving too quickly to enter the target system. The population would face a crisis shaped by work performed hundreds of years before their birth. They might attempt repairs, alter the trajectory, or accept passage through the system without settlement. The engines would therefore hold symbolic importance. They represent the ship's ability to transform endless movement into arrival. Generations might maintain them with ceremonial discipline, aware that most inhabitants would never witness their full operation. Radiation outside Earth's magnetic protection would affect the mission continuously. High-energy particles can pass through hull material, damage DNA, alter electronics, and create secondary radiation during collisions. 1,000 years provides many opportunities for exposure and cumulative harm. The vessel would surround living areas with thick shielding. Water, food reserves, industrial material, and waste awaiting processing could be placed around habitats. Some sections might lie deep inside a rotating structure, protected by several layers of equipment and mass. Passengers could retreat into highly shielded chambers during intense radiation events. Shielding changes as resources move. A water tank emptied for maintenance no longer protects the same area. A warehouse gradually consumed by manufacturing loses mass. The ship's design would need to preserve protective distribution as materials circulated through the economy. Radiation would also influence reproduction. Damage to reproductive cells could increase mutation and health risks across generations. Medical systems would monitor exposure throughout every life. People working near the outer hull might face strict limits and long recovery periods inside protected zones. Gravity would shape every body born during the voyage. A stationary vessel offers microgravity unless rotation creates an artificial downward force. Long-term weightlessness affects bones, muscles, circulation, vision, balance, and many other systems. A civilization living for centuries would probably require rotating habitats. A ring or cylinder could turn around the ship's axis, pressing inhabitants toward its outer surface. The strength of artificial gravity would depend upon rotational speed and distance from the center. Large structures allow gentler rotation, reducing disorientation and unusual effects during movement. Building and maintaining the rotating sections would be difficult. Bearings or magnetic systems must support enormous mass. Imbalance could create vibration. A damaged habitat might alter the distribution of weight and threaten structural stability. The crew would monitor rotation with the same care given to atmospheric pressure. Different areas could provide different gravity levels. Workshops near the axis might experience very little, while residential districts farther outward approached Earth-like conditions. Children would learn to move between these regions. Sports, architecture, and transport would develop around a geometry unknown to planetary life. The human body might still change across generations. Artificial gravity may not reproduce every feature of life on Earth. Radiation, diet, controlled microorganisms, limited sunlight, and reproductive selection would create a new biological environment. Small effects could accumulate through centuries. Medical records would reveal whether bones, hearts, immune systems, pregnancies, and childhood development remained healthy. Treatments could compensate for certain problems. Exercise, medication, genetic screening, and carefully designed nutrition would become routine parts of life. Deliberate genetic modification might eventually enter the debate. Engineers could correct inherited disorders or improve resistance to radiation. Changes intended to protect one generation could become permanent features of the population. The distinction between medicine and adaptation would grow uncertain. Some inhabitants might argue that humanity should remain biologically suited to the destination planet. Others could accept adaptation to the ship because the vessel was the only world anyone currently inhabited. The bodies of future children would become a field where loyalty to Earth, survival during transit, and preparation for arrival competed. A viable population would require careful demographic planning. Too few births would create an aging society and labor shortages. Too many could exceed food and habitat capacity. Births would need to remain distributed across time so that each generation contained enough adults to support the others. Genetic diversity would also matter. A large founding population would reduce the risks associated with shared ancestry. Frozen reproductive material could introduce additional lineages during later centuries. Detailed genealogies would guide reproductive medicine and help avoid harmful concentrations of inherited conditions. These systems would enter private life. Couples could receive genetic advice when planning children. Some combinations might carry greater risk. Stored reproductive material or embryo selection could offer alternatives. The society would need to balance collective survival with personal autonomy. A demographic plan can predict numbers and remain unable to create desire. Adults must choose to raise children within a confined world. Their willingness would depend upon trust, security, working conditions, relationships, and belief in the future. Population stability would emerge from social health alongside medical capability. Pregnancy and childhood would carry unusual importance. Every child represents a person, a future worker, a potential parent, and a connection in the chain leading toward arrival. Excessive attention could turn childhood into a period of institutional pressure. The ship would need maternity care, neonatal medicine, pediatric specialists, educators, and safe environments for play. Children require opportunities for exploration even when the surrounding world contains airlocks, machinery, and hazards. Residential districts might include adaptable spaces that change as the number and ages of children shifted. Parents would face duties to their families and to the vessel. Work schedules might be arranged around communal care. Several adults could share responsibility for groups of children, reducing the burden upon individual households. Family structures could become broader than those common at departure. Each generation would interpret parenthood differently. Some might see it as a contribution to the voyage. Others would pursue it through love and personal meaning. During periods of crisis, the society might pressure adults to delay or increase births. These moments would test whether the mission respected the people whose lives sustained it. Microorganisms would be among the most rapidly evolving passengers. Bacteria, fungi, and viruses reproduce quickly, responding to the chemical and biological conditions inside the ship. Human bodies depend upon diverse microbial communities, while other organisms cause disease or damage equipment. The vessel could begin with a carefully selected microbiome distributed across people, crops, soil substitutes, waste processors, and industrial systems. Isolation would create a unique ecosystem. Certain species might disappear accidentally. Others could become dominant after finding a favorable niche inside ventilation ducts or water lines. Medical teams would monitor microbial change through continuous sampling. Antibiotics would be used cautiously because resistance could develop and persist within the closed environment. New treatments might include targeted viruses, engineered microbes, immune therapies, and environmental control. A pathogen introduced at launch could transform across centuries. A harmless organism might acquire damaging traits. A useful microbe could lose a function essential to nutrient recycling. Biological management would require the same long-term attention given to reactors and engines. Infectious disease would spread quickly through a connected population. Compartments and quarantine protocols could slow transmission. Medical isolation would still be emotionally difficult in a society where every person occupied a limited social network. The ship would need the capacity to create medicines after departure. Stored drugs expire and degrade. Manufacturing antibiotics, anesthetics, hormones, vaccines, and complex biological therapies requires specialized equipment and knowledge. Medicinal plants and engineered microorganisms might supply some compounds, while laboratories produced others. Surgery would remain necessary. Accidents, childbirth complications, cancers, and organ disease would occur throughout the voyage. Robotic systems could assist, though trained medical professionals would need to interpret unexpected situations. Every generation must educate new surgeons, nurses, pharmacists, and researchers. Rare conditions would pose a challenge because no specialist population existed beyond the hull. Artificial intelligence could preserve diagnostic knowledge from Earth, compare cases with vast archives, and guide treatment. The final decision would belong to people working with the materials and equipment available aboard. Education would determine whether the ship remained technologically capable. Children would need broad cultural learning alongside rigorous preparation for essential work. The curriculum would include mathematics, language, history, ecology, medicine, engineering, manufacturing, governance, and the practical systems of the vessel. Learning could begin through direct contact. Students might visit water plants, gardens, workshops, and control rooms throughout childhood. Every citizen would understand basic emergency procedures. Specialization would develop later, guided partly by interest and partly by the needs of the population. The society would need enough freedom for talent to emerge. Assigning a child to a profession too early could waste ability and create resentment. Allowing every person complete vocational choice could leave critical roles unfilled. Educational planners would navigate this tension continuously. Apprenticeship would preserve knowledge that manuals cannot capture. Experienced technicians would teach the sounds, textures, and patterns associated with machinery. Physicians would pass on judgment developed through years of practice. Farmers would recognize subtle signs of crop stress before sensors confirmed them. Digital archives could contain a large portion of Earth's knowledge. Scientific literature, art, music, languages, films, engineering designs, medical records, and historical testimony would be carried into the voyage. Preserving the files would require regular copying, verification, and migration into new systems. A perfectly preserved archive could still become culturally inaccessible. Languages change. Technical concepts lose context. An old engineering document may assume tools and materials that no longer exist aboard. Curators would update explanations while protecting the original information from distortion. The quantity of knowledge would exceed the attention of any generation. Selection would become unavoidable. Life support science and current ship history would occupy much of education. Ancient literature or specialized research fields might survive inside storage while receiving little study for centuries. Artificial intelligence could guide people through this abundance. It might translate old languages, reconstruct obsolete tools, and answer questions using records created before launch. Its own models would require maintenance and scrutiny. A system trusted as the voice of the founders could acquire authority far beyond its intended role. History aboard the ship would grow until it competed with the history of Earth. The first century might be dominated by stories of departure. The fourth would study reactor crises, constitutional reforms, migrations between habitats, and conflicts whose consequences shaped current law. Every generation would add heroes, failures, taboos, and unresolved grievances. A technician who prevented decompression could become a civic symbol. A council that imposed harsh reproductive controls might remain hated centuries later. Sections of the vessel could carry names linked to events whose physical traces had disappeared. Historical interpretation would influence political legitimacy. Leaders might invoke the founders when defending authority. Reformers could cite forgotten provisions from the original charter. Competing groups would select different moments from the archive to explain what the voyage was meant to become. The mission would survive more easily if history remained open to examination. Suppressed records create myths that can collapse suddenly when evidence emerges. A society traveling through interstellar space would need the emotional strength to acknowledge earlier mistakes without losing confidence in its future. Language would evolve naturally. Pronunciation changes, new words appear, and old meanings drift. Terms connected to weather, landscapes, and animals might survive mainly through archives. Vocabulary related to rotation, air systems, recycling, and ship geography would enter everyday speech. Different habitats could develop accents and dialects. Communities separated by work schedules or physical distance might create distinct expressions. 1,000 years provides enough time for mutual understanding to weaken unless education and communication maintain a shared language. Preserving linguistic diversity from Earth would require deliberate effort. Families could teach ancestral languages through stories and ceremonies. Some would remain vibrant, others might survive only in songs, names, and inscriptions whose full meaning became uncertain. A common operational language would support safety. Emergency instructions, technical manuals, and cross-habitat communication need clarity. The society could preserve variation in cultural life while maintaining strict standards in critical environments. Isolation would shape every mind. No passenger could leave the vessel permanently without entering lethal space. The nearest human society might be centuries away by radio, assuming Earth remained capable of communication. Every dispute would occur among people who continued sharing the same closed world. Privacy would need architectural protection. Individuals require places where they can withdraw from family, colleagues, and public attention. Habitats would include quiet rooms, gardens, artistic spaces, and virtual environments. Constant observation for safety could become psychologically oppressive. Crowding would vary across the journey. A growing population could make residential areas tense and noisy. A declining population might leave vast empty districts whose silence carried its own burden. Social design would need to adapt as numbers changed. Mental health care would be considered essential infrastructure. Counselors, community mediators, recreation, meaningful work, sleep protection, and opportunities for personal development would reduce strain. The ship would need to support ordinary human imperfection without allowing individual crises to endanger critical systems. Relationships would unfold within a population where everyone remained connected through several social networks. Former partners could continue working together for decades. Family conflicts might affect professional teams. Political opponents could share grandparents and live in neighboring compartments. A large enough population would provide social variety and reduce the intensity of these connections. People could form new friendships and move between districts. Cultural events, education, and temporary work assignments would bring communities together. The vessel might establish new customs around separation and reconciliation. Mediation could become more important than punishment for ordinary disputes because permanent exclusion wastes human potential. Restorative practices might help communities continue functioning after harm. Serious violence would still occur. The ship would need law enforcement, secure areas, courts, and systems for protecting victims. Imprisonment consumes labor and habitat space, while unrestricted, dangerous behavior threatens everyone. Justice would evolve under constraints unknown to societies with open territory. Government at departure might be designed carefully by legal scholars, engineers, psychologists, and future passengers. The charter could distribute power among elected councils, technical authorities, courts, and independent oversight bodies. Emergency procedures would specify who controlled life support during a crisis. 1,000 years would expose every weakness. Temporary emergency powers might become permanent. Technical experts could acquire political dominance because only they understood critical systems. Popular governments might ignore long-term maintenance to satisfy immediate demands. Courts could struggle to enforce limits during existential danger. The Constitution would need a method for revision. Descendants should be able to adapt institutions to conditions the founders never foresaw. Revision must also protect the ship against impulsive decisions that threaten survival. Some principles would require broad agreement across habitats and generations. Legitimacy would depend upon participation and transparency. Citizens are more likely to accept restrictions when evidence is available and decision-makers share the burden. Secret demographic models, hidden shortages, or privileged access to resources could destroy trust quickly. Technical authority would create a particular political risk. Engineers might warn that a reactor requires shutdown, reducing available power for several years. Citizens without specialized knowledge would have difficulty evaluating the claim. The decision could affect housing temperatures, food production, and industrial employment. Independent teams could review major technical forecasts. Data would be public whenever safety allowed. Education would give citizens enough scientific understanding to follow debates. These practices would slow decisions while reducing dependence upon a narrow professional class. Experts themselves would disagree. One team might prefer a cautious repair and another accept greater risk to preserve resources. Political values enter engineering whenever several solutions distribute danger differently across time or population groups. The society would need a culture capable of respecting expertise without treating it as unquestionable authority. Survival would require technical truth and democratic legitimacy to remain in conversation across centuries. An economy would emerge around access to labor, space, energy, food, and manufactured objects. Currency might help coordinate personal choices, though essential resources would remain regulated. Nobody could be allowed to purchase all available oxygen or control a critical water system. Private possessions could provide comfort and identity. Clothing, art, furniture, tools, and personal rooms would matter deeply in a world where every object had traveled through generations of recycling. Certain items from Earth could acquire enormous symbolic value. Inheritance would create inequality unless carefully managed. A family occupying a desirable habitat for centuries might gain social influence. Technical professions could become associated with particular lineages. Access to education and reproductive opportunities might reinforce these divisions. The ship would need mechanisms for mobility and shared ownership. Public systems should remain accountable to the whole population. Personal initiative could support innovation, craft, and cultural variety. The balance would shift during crises and periods of abundance. Social classes could form around proximity to power, control rooms, gardens, education, or safer regions of the vessel. Habitats with stronger radiation shielding might become more desirable. Families connected to senior engineers or government officials could secure advantages. Small inequalities can deepen across generations. Better nutrition, quieter housing, and access to specialized education influence health and opportunity. A society whose survival depends upon cooperation would still contain familiar human struggles over status and privilege. Visible unfairness could damage motivation. People performing dangerous maintenance may reject sacrifices demanded by leaders living in comfort. Reproductive restrictions would provoke anger if applied differently across social groups. A closed world leaves few places for resentment to disperse. Strong public institutions could limit these divisions. Transparent allocation, rotation of responsibilities, universal education, and equal access to medicine would protect cohesion. The ship's stability would depend partly upon whether inhabitants considered its burdens legitimate. Culture would give emotional shape to the voyage. Music, stories, visual art, games, festivals, and rituals would transform machinery into a human world. The first generation might create works about Earth and departure. Later centuries would draw inspiration from ship history, artificial landscapes, and the surrounding stars. Artists would preserve experiences that technical records overlook. A song could capture the fear of a reactor shutdown. A novel might explore the life of a child assigned to a profession. Murals could cover repaired walls with images linking each patch to the generation that installed it. Festivals would organize time during a journey without natural seasons. Departure Day might mark the beginning of the civic year. Agricultural celebrations could follow major harvest cycles. A ceremony performed every decade might honor those who died maintaining the vessel. Culture would continue changing because stability cannot mean emotional stillness. A society forced to imitate the founders for 1,000 years would become brittle. The voyage needs continuity spacious enough for descendants to create lives belonging to their own era. religion, and philosophy could help passengers interpret their place between worlds. Earth might be remembered as a sacred origin. The destination could become a promised land. The ship itself might be understood as an ark, a living ancestor, or a moral community carried through cosmic darkness. New beliefs would emerge from ship conditions. Air, water, and cultivated soil might acquire ceremonial meaning. Maintenance work could be associated with service to future generations. Death rituals might return bodies to the ecological cycle, joining spiritual ideas with material necessity. Different traditions could coexist for centuries and sometimes come into conflict. A movement might demand strict fidelity to the original mission. Another could argue that the living population had the right to choose a new destination. Beliefs about reproduction, genetic modification, and artificial intelligence would influence law. The society would need ways to protect conviction and peaceful disagreement. A voyage this long cannot depend upon one worldview remaining dominant. Intellectual diversity may create tension while also providing alternatives when old assumptions fail. Communication with Earth would weaken as the ship traveled farther. Messages might initially take months or years to arrive. Eventually, a question and answer could span generations. The people sending a report might be dead before Earth received it. News from the solar system would describe an increasingly ancient past. Earth could change beyond recognition while the ship continued receiving delayed images of familiar nations and institutions. The connection would resemble an archive arriving gradually through space. Earth might transmit scientific discoveries, cultural works, and engineering designs useful to the mission. The ship would send observations, demographic reports, and records of its own history. Each side would influence the other without sharing a common present. Silence could come through distance, technical failure, political choice, or catastrophe. The ship might continue transmitting toward a world that no longer answered. Its inhabitants would have to decide whether Earth remained part of their active society or had become part of history. The destination would also exist in the past. Telescopes observe distant planets through light that has traveled for years. During a 1,000-year voyage, the target system continues changing. Its star evolves slowly, while planetary climate, geology, and possible life can transform more quickly. The ship would study the destination continuously as it approached. Instruments would reveal finer details. Atmospheric chemistry, weather, moons, magnetic fields, and surface conditions would become clearer. Early assumptions could prove wrong centuries after departure. A planet considered habitable might possess toxic chemistry or dangerous biology. The system might lack accessible resources needed for settlement. The crew could alter course toward another destination, adding centuries to the journey. Changing course would provoke political and emotional conflict. Generations may have organized their lives around arrival at one world. Abandoning it would redefine the meaning of every earlier sacrifice. Continuing toward a dangerous planet could satisfy tradition while placing the living population at risk. Motivation would decline during periods when arrival remained impossibly distant. The first passengers chose the mission. Their descendants inherited it. By the 5th century, the launch might feel as remote as medieval history feels today, while several centuries still remained. People would ask why they should devote their lives to a goal they would never witness. Maintenance work offers immediate survival, though preparation for arrival serves distant descendants. Projects lasting longer than one lifetime require trust that later generations will continue them. The society could divide the voyage into meaningful stages. Each century might have major objectives: expanding habitats, improving genetic health, rebuilding engines, mapping the destination, or restoring ecological diversity. People need achievements visible within their own lives. The ship itself could provide a full human existence. Relationships, learning, art, work, and community would give life value independently of arrival. A mission culture focused entirely upon the destination might make every present generation feel disposable. Stability would grow from treating life during transit as worthy in itself. Loss of motivation could appear through neglect. Maintenance schedules would be postponed, students would avoid demanding professions, families might have fewer children. Citizens could regard warnings as exaggerated because previous generations had survived similar predictions. A slow decline is difficult to confront. The ship may continue functioning while reserves shrink and repairs become less reliable. Each year appears manageable. The accumulated loss becomes visible only after several decades, when restoring earlier capacity requires more labor than the population can provide. Leaders might respond with propaganda and punishment. Compulsory work could preserve essential systems temporarily. Coercion would deepen resentment and weaken trust. A society capable of surviving a millennium needs motivation rooted in participation, fairness, and genuine purpose. Periods of cultural renewal could reverse decline. A generation might rediscover neglected knowledge, restore damaged habitats, and create new institutions. The ship's history would contain several moments when collapse appeared near and collective effort changed the trajectory. Conflict could become catastrophic because every faction occupied the same physical system. Sabotaging power, water, or air would threaten supporters and opponents together. Political leaders would need to keep critical infrastructure outside ordinary struggles for control. Habitat sections might possess limited autonomy, allowing communities to govern local affairs. Essential systems would require shared standards and mutual inspection. A federation could reduce the concentration of power while maintaining the cooperation needed for navigation and life support. Secession would remain difficult. A community could seal its habitat and operate separate schools, laws, and cultural institutions. It would still depend upon shared energy, manufacturing, and external protection. Complete independence might require dividing the ship physically, a dangerous process with irreversible consequences. Civil war could destroy centuries of preparation in a few days. Weapons capable of piercing walls or damaging machinery would be tightly controlled. Security systems would need to prevent violence without creating permanent authoritarian rule. Accidents would test whether the society could act as one community. A major fire might force thousands of people into neighboring habitats. Crop areas could be destroyed. Workshops and archives might disappear. The survivors would face years of reduced living space and increased labor. Emergency plans would be practiced throughout life. Children would know evacuation routes. Each district would maintain independent supplies and medical capacity. Leaders would rehearse decisions involving compartment loss, epidemic, reactor failure, and navigation damage. Real emergencies would still differ from simulations. Communication systems might fail. Several crises could occur together. A fire could damage power while smoke contaminated crops and blocked access to medical facilities. Recovery would continue for generations. People born after the event might grow up repairing its consequences. The disaster would enter law, culture, architecture, and family memory. Stability across 1,000 years would involve the ability to absorb shocks without freezing society permanently around them. The greatest danger might come from several modest failures interacting. A reduction in power lowers agricultural output. Food restrictions increase stress and weaken health. Illness reduces the maintenance workforce. Repairs are delayed, causing further power loss. Births decline as families lose confidence. Complex systems often fail through cascades. The ship would use sensors and models to detect early warning signs across technical, biological, and social domains. Engineers, physicians, farmers, and demographic planners would share information because their systems were inseparable. Decision-makers would need to act before danger became visible to everyone. Preventive measures can appear unnecessary when they succeed. Citizens may resent restrictions based upon projections. Transparent evidence and institutional trust would determine whether early action remained politically possible. Resilience would come from spare capacity. Extra food, unused habitat, redundant workers, genetic reserves, and alternative power systems appear inefficient during stable periods. Their value emerges when several failures arrive together. Artificial intelligence could coordinate the immense complexity of the voyage. It would monitor millions of sensors, predict component failure, model population changes, guide medical treatment, and maintain historical records. Its advice could save the ship repeatedly. Dependence would create risk. An error in the system's model might influence every layer of planning. A corrupted update could spread through redundant copies. The population might lose the ability to challenge recommendations expressed with mathematical confidence. Several independent systems could review one another. Human councils would retain authority over moral and political decisions. The artificial intelligence would explain assumptions, uncertainty, and alternative outcomes informed citizens could examine. Across centuries, the system itself would change. Engineers would modify its architecture, train it on new cultural data, and replace hardware. The intelligence speaking during the final year might share only partial continuity with the one launched from Earth. It would become another evolving institution aboard the ship. The passengers might eventually decide that the ship itself had become their permanent home. After 700 years, its habitats would contain ancestral graves, historic districts, mature ecosystems, and cultural traditions rooted in the vessel. The destination planet would remain unfamiliar and potentially dangerous. Landing would require exposure to uncontrolled weather, gravity, soil chemistry, microorganisms, and landscapes extending beyond every monitored boundary. People adapted psychologically and physically to the ship might fear the open world their ancestors desired. A political movement could argue for remaining in space, using the target system's asteroids and moons to expand the vessel. Another group would see settlement as the fulfillment of the mission. The debate would concern identity as deeply as safety. Survival during transit does not guarantee agreement about arrival. A society stable enough to cross 1,000 years may have changed enough to reject the purpose that placed it there. Respecting that change could be part of the voyage's success. If the population chose to land, preparation would begin generations in advance. Probes would enter the system first, mapping hazards and collecting samples. Robotic factories could build shelters, power plants, and landing infrastructure before human arrival. The ship's inhabitants would train for planetary conditions. Gravity levels might be adjusted gradually. Simulated landscapes would expose people to wind, irregular terrain, natural light, and wide horizons. Medical teams would study how bodies developed in artificial environments responded to the planet. Ecological caution would be essential. Native life, if present, could interact unpredictably with human biology and Earth organisms. Contamination could damage the destination and threaten the settlers. Quarantine might continue for decades after arrival. The generation reaching the planet would carry the accumulated decisions of everyone who kept the vessel alive. Their first step would depend upon farmers, engineers, teachers, parents, and repair crews who died centuries earlier without seeing the star grow bright. Survival for 1,000 years would require population large enough to absorb accidents and preserve social variety. It would require genetic archives without allowing reproductive planning to erase personal dignity. It would require machines designed for repair, industries capable of rebuilding those machines, and knowledge transmitted through periods of progress and decline. The ecosystem would need to recycle air, water, nutrients, and material with extraordinary efficiency. Reserves would provide protection against imperfect cycles. Separate habitats would prevent one biological or technical failure from spreading through the entire vessel. Government would need stability and revision at the same time. Laws should protect essential systems, distribute burdens fairly, and allow descendants to reshape institutions. Education would preserve technical competence while giving children lives larger than the professions assigned by demographic necessity. The society would also need joy. Music, friendship, privacy, love, humor, art, celebration, and curiosity would carry people through years when the destination remained only a point of light. A population can endure sacrifice for a time. A civilization requires reasons to remain alive beyond sacrifice. The ship approaching its final century would contain almost no material untouched by the voyage. Components would have been melted, shaped, used, dismantled, and shaped again. Water would have passed through countless bodies. Gardens would descend from seeds regenerated through hundreds of harvests. The population might speak a language transformed from those heard at departure. Their faces would carry ancestry from the founders and from genetic archives opened across the centuries. Their institutions would bear traces of revolutions, reforms, emergencies, and acts of reconciliation. In the oldest chamber, a preserved window or display might show the final image of Earth recorded during departure. Children would see the blue planet and understand that everyone aboard descended from people who once lived beneath its sky. The image would carry history without offering personal memory. Ahead, the destination star would finally appear brighter than the surrounding field. Its planets would become real landscapes on observation screens. Arrival would move from inheritance into experience. The final generation, born entirely between the stars, would live through a transition no previous generation had known. Their parents would have prepared them for a planet. Their grandparents might have doubted that arrival would occur during any living person's lifetime. Engines preserved through 10 centuries would awaken fully. The ship would turn and begin surrendering the velocity carried across the darkness. Vibrations would travel through structures repaired by hundreds of generations. Every alarm would be studied with fear because the vessel had only one chance to slow. The passengers would watch the target system expand around them. Moons would acquire phases. Planets would move visibly against the stars. Communication delays would shrink from years to hours, and then minutes between probes and the ship. For the first time in a millennium, humanity aboard the vessel would possess access to new matter, new energy, and new territory. The closed arithmetic of the journey would begin to loosen. Every resource would no longer need to originate from the ancient inventory carried away from Earth. Whether humanity survived would depend upon the meaning assigned to survival. The people arriving might differ culturally and biologically from those who departed. The original nations could be forgotten. Religions, languages, and political systems might have transformed. Most launch-era machines would exist only in museums and diagrams. Continuity would remain visible through bodies, records, knowledge, and the vessel itself. Each generation received life from the previous one and passed forward enough of the world to allow another generation to exist. Survival across a millennium would resemble a flame maintained through changing hands. The mission could succeed after abandoning parts of its original design. A different destination, altered biology, revised government, and a rebuilt ship might all become necessary. Endurance would depend upon adaptation guided by memory. A civilization remaining perfectly unchanged for 1,000 years would struggle to respond to reality. The viable society would preserve its essential responsibilities while allowing almost everything else to evolve. The answer may ultimately lie in the way the voyage is imagined. A ship designed as a temporary container would place every generation in a waiting room. Their lives would be measured against an arrival belonging to distant descendants. Frustration and neglect would grow inside a society asked to treat the present as a corridor. A ship designed as a genuine world would offer complete lives during transit. Its inhabitants could build relationships, create art, pursue discoveries, transform institutions, and find meaning within the journey. Arrival would remain important without reducing the centuries before it to delay. Machines would still fail, crops would suffer, governments would make mistakes, families would disagree about children and duty. Some generations would inherit abundance and others hardship. The society's strength would come from its ability to recover without demanding perfection. Humanity has never maintained a sealed civilization for 1,000 years. No experiment can reproduce the full duration before launch. The mission would begin with knowledge, models, and safeguards, then enter a future filled with events no planner could foresee. 1,000 years after Earth disappeared, an engineer might enter a narrow chamber near the center of the ship. The room could contain a pump whose casing had been replaced dozens of times while part of its basic design remained recognizable from launch. She would open it using tools manufactured aboard, examine a component created by her grandparents, and install a replacement produced that morning. Elsewhere, Children would study the destination planet. Farmers would inspect routes beneath artificial light. Musicians would rehearse for a festival marking the 999th year of the voyage. A council would debate the laws that would govern the first settlement. None of them would have chosen to leave Earth. Each would possess the ability to decide what happened next. Their society would have crossed the centuries through countless ordinary acts performed by people whose names no archive could preserve completely. The ship would remain alive because generations continued repairing it. Humanity would remain alive because generations continued raising one another. A 1,000-year interstellar mission would stand among the most difficult projects any civilization could attempt. Its engines would need to move a world. Its hull would need to survive the space between stars. Its ecosystem would need to recycle the substance of life through generations. The harder requirement would live inside the population. People would need to accept dependence without surrendering freedom. They would need to preserve expertise without freezing culture. They would need to honor the founders without granting the dead permanent control over the living. The voyage would contain crises severe enough to make extinction appear close. Recovery would depend upon redundancy, knowledge, fairness, and a willingness to continue working for descendants separated by centuries. Every successful generation would inherit a fragile world and leave it slightly more prepared for the next. Could humanity survive 1,000 years between the stars? Physics offers no simple prohibition. Biology provides narrow margins. Engineering demands a vessel capable of rebuilding itself. Society carries the widest uncertainty. The ship could cross the darkness. The survival of its passengers would depend upon whether they learned to make the darkness a place where human life could continue.